for area. Yep. Yep. Okay, so there's 1 and 2. So number 1 I got, hey, you can't see anything yet. There you go. There's number 1, 14.693. I've got the integral to go along with that. So, gosh, if it started off with 500 gallons, now there's only 14.693. That means it's obviously lost a lot, right? That means R of t is very much overpowering A of t on this interval. So 14.693. I would say that what I've written up there would be the minimum you would put for some quiz or test as far as credit goes. We're going to show your setup, show your answer. The calculator's active, so you should use that. Number 2, based on basically multiplicity, I found that G prime never goes positive until 5 and above. So I said G was increasing on 5 to infinity because G prime is positive on 5 to infinity. Any questions on 1 or 2? Okay, here's number 3. So I got 1.083. I don't know if that changed.
I just hadn't done the second part yet.
Oh, you said that one chunk. Okay, gotcha. So I cut you mid-problem.
Yeah.
I guess that other little sliver of area really wasn't that much area,
Yeah.
right? Just a tiny bit. Please excuse my bad scaling on my drawing. X equals 0 should probably be on the y-axis. It's not, though, somehow, but it should be. Nobody in the other class noticed that. Just kind of waited. I think I just drew the picture and then threw the y-axis in there, and I was like, oh, never mind.
Close enough.
Close enough, right? Yeah, I guess. I don't know. It's not very good. Anyways, I think the number is good. I think the setup is good, but just ignore the picture. Okay. Questions on 3? Okay. So then probably good timing to remind you of your area quiz. Concept 19 is tomorrow. And we'll proceed as normal through the, kind of the rest of the material. Wednesday will be just a full review day. Thursday is the Unit 6 test. Did you guys see the email I sent out this morning?
Yes.
Okay, with all the review topics that are on the Unit 6 test. So, just let that focus your review studying. And of course, as I mentioned in the email, there will be some material from Unit 6, like slope fields, differential equations, and that sort of thing. Okay, we doing all right? Okay, so if you are not already awake, I hope that this next thing will wake you up. We have a little demo, and I hate to say, we did this demo in my other section, and it was really choppy, and it was not as good as I wanted it to be, so we'll see. We'll see how it goes this time. So this is a little GeoGebra app, and can you see how, we found areas of things like that yellow region before, 2 minutes ago? So what we're going to be doing here, I mentioned this is our final concept, is concept 20, and concept 20 is volume. And of course, we're not talking about how loud the stereo is, we're talking about how much displacement something has, right? Like how much stuff there is within a solid. So when you find area is of a 2-dimensional figure, right? But how do you find the volume? What do you need? 3-dimensional figure, yeah, like a length and a width and a height. We need to add in that 3rd dimension. It's not just 2 dimensions like we have with area. So I want to explain how it is we're going to get that. So I'm going to, knowing where we're going to go, I'm going to change this function a little bit. I'm going to go, I think this is what I did before. Let's go I think we'll go with that. That's a pretty interesting looking area. We're not doing area today, we're doing volume. So I'm going to make some adjustments here. I'm going to make it really simple for us today. I'm going to make g of x 0. And I'm going to go 1 to 7 here. So I've just settled on this much more simple looking region. So just take a second and look at that. You can look at either side. The one on the right is going to be the side that animates. The one on the left is just going to be the graph of the, obviously you can see it's a parabola. So the question is, like I said, how on earth are we going to get volume, right? How are we going to get this three-dimensional figure? So we're going to look at it in two different ways in our final concept here. And the first way we're going to basically get volume is through rotation. Rotation. Let me show you what I mean by that. Let's do, oh, come on, computer app. Okay, you're off to maybe a better start. Okay, I think you are. So check this out. I'm going to do some revolution. So carefully watch the graph on the right. See how this goes. Can you see it start to revolve? It's supposed to be all smooth. I blame this on the kids in the hall that are watching Netflix. And when you talk to them later, say, hey, did you study for your quiz? They're like, no, I was too busy. Okay, yeah, that's my reaction too. I'm like, oh, interesting. Oh, you see it starting to revolve now? This is supposed to be smooth animation, but it is sort of choppy. You guys are going to get the less high-tech version later. Can you see it starting to go? So it's revolving. Can you see how that parabola is revolving around the x-axis very slowly, but it's revolving? Go, computer, go. You can do it. So I'll cheer for the computer. Eventually it's going to get all the way around. I haven't told it to get there yet, but I will. Yeah, boy, oh boy, it's really slow. It's like watching turtles do the 100-meter dash. You know, you're like, and go get lunch and come back, and it'll still be. You get the idea. So what I really want to do here, I want to get this full solid. Let's give us time to chat. Are you seeing this revolution? See what I mean? How this yellow region is revolving around the x-axis. It's almost like it's leaving a image of itself as it revolves and sweeps out this volume. What I really want to do, come on. It's slower than before. There's more kids on Netflix. Funny, a few years ago when we were looking at IT and internet and stuff, there was this proposal floated of, hey, is it possible for you to like block things like Netflix? You know, obviously via like somebody wants to go cellular, I mean, whatever, but is there any way to block that? And like, oh yeah, we could totally block that. It's like, well, why don't you? And the response was basically, people would get mad. Like, YouTube, but not Netflix? Yeah. Good for them. Yeah. It's funny, YouTube. Interesting. Guys, this is like horribly slow. Can you see what's going on here? Kinda? Sorry, it's like a whole macro in a circle. But the key here, hey, listen, the key to recognize here is that this solid is really solid. You know how like macaroni has a hole through it? It's not really a macaroni. So like, let's take a second and try, listen up please. I don't think macaroni is really a good description because of the solidness of this. Can you think of a different, like, physical description for what this is? Well, it's not really a washer because don't washers have holes in the middle? A disc. Okay, so a cookie, but a Frisbee has like that hollowed out part. A cookie, a what? A cheese wheel. That's not bad. A cheese wheel, but it's like got rounded. It's got rounded edges, right? Like a cheese wheel. I was thinking sort of like a yo-yo, kind of. I realized the yo-yo has the place where the string goes, but like sort of a yo-yo. Yeah, it could be. Yeah, yeah. This thing is just like stuck here, isn't it? It's a bummer. Oh, look at that. Could you think of it as like a perfectly symmetrical egg? Kind of? Sort of? A what? Say one more time? A Mento. Yeah, like those are nice and smooth. Yeah, like a little mint thing. Yeah. Okay. Man, oh man. Do you have one? Oh yeah, like Hayden. So if you just, yeah, like if you just took your yo-yo and just continued this on up. Let me see. That's not bad. That's fast. All right, man. There's so much more I can do with this if it would let me, but it's like not reacting to my input at all. It's just sitting there. Oh, look at that. Do you see what I just did? Whoa. I can move it around. Look at the yo-yo like thing from different angles. So can you see how this is a solid? All this really is a visualization exercise. Now it looks like a Pac-Man. Can you see how the revolution is not yet done? This might be worthwhile. Can you all see the parabola right there? It does look like a Pac-Man. So this is the parabola. I'll highlight it for you in a really light color. The parabola does this. Does that make sense? You see the parabola sweeping out the volume? Okay, so you're good. So apologies for the mediocre performance of the app there. Okay. So you guys have seen the not very well working high-tech version. You're about to see the very low-tech version. Hopefully one or both will help you. So if we have a solid like that, like I mentioned, we're going to be finding its volume. To find a volume of something like that, we are going to use what's called the DISC method. D-I-S-K. Someday when you guys have kids, they'll have no idea what a CD is or what a DVD is. But you do, right? What does the D stand for in CD? Disc, compact disc. DVD, right? Disc, right? So we're talking about discs really similar to a CD, right? Except there's no hole in the middle. Like a CD has a little hole in the middle. These won't have any hole in the middle. Why is it called that? I would like to show you using a very similar looking graph. Okay, so what I've drawn in there is a representative rectangle, and this is really similar to what we did with area. I'm going to take this, just like we did in that little animation, we're going to rotate this around the x-axis. So I usually will draw something like this in to help me remember what I'm revolving around. And this might take me a try or two, but I will do my best. As I revolve this around, I'm going to get Can you see this? So, Anna, please excuse if my scaling is slightly off. Why is it so tall? It's a little grotesquely tall, yes, I will give you that.
I didn't know if there was like a mathematical reason for it.
No. I just decided to give it 1 or 2 tries instead of like 9 tries. You know what I'm going to do? I'm going to try it again on a different one. So check this out.
That's awesome. what I thought.
She's so good at drawing clouds, she feels like she can be critical of my math drawing. And all in good spirit, right? Okay, so here we go. I'm going to give it another shot.
This is kind of tripping me out.
Do we have to do drawings like this?
Nope.
It's like this is your next test. This is so hard.
Do it wrong.
It would be very helpful for you if you could visualize this.
I can visualize it's just like kind of hard to.
Well, you just are starting, right? You're just beginning. So you might not be very good at it yet. Now that red one, Anna,
But the double lines help.
that red one,
Yeah, it looks awesome.
pretty good, right? I got the Anna approval. So good.
Your life is complete.
It pretty much is. See, guys, I'm out. Have a good rest of your. No, I'm just kidding. I get to hopefully, someday I'm speaking with Jesus, and he's like, "By the way, why did you quit teaching so early?" I'm like, "Well, Anna gave me her approval, so I just thought I better just quit while I'm ahead." And Jesus will say, "I get it. Makes sense." Oh. Anyways, I don't know what he would say. I say, "What is your problem?" Okay, so here's another one. Oops, I'm going to go from here. I'm going to try not to mess up my good track record. Oops. Yeah, so obviously you could try to draw them all in, but eventually it would just get way too cluttered. Mine is starting to get cluttered. Can you see how if you rotate these representative rectangles around, you get these discs? Don't these look like CDs with no hole in the middle? Okay. So then let's think about this very conceptually for a second. We can talk about formulas all you want here in just a moment. But conceptually speaking, if I wanted to get the exact volume, like I tried to do with that little animation earlier, how many of these representative discs would I need? I'd need an infinite number of them. And how wide would they need to be? Approaching what? Infinitesimally wide, approaching zero width, right? So if I'm going to pack all these in here, they need to approach zero width. There needs to be a number of them approaching infinity. How in the world do I take an infinite number of really skinny things and add them up? It would take forever, or I could just use... Oh, come on. How do I add up a bunch of really, really skinny things? Definite integral, right? It's got to be the definite integral. Before we do anything with the definite integral, I would like to, again, at the risk of messing up, I'm going to take the red disc. Oh, now that one is much better. I'm going to take the red disc. I'm going to bring it out here. I'm going to put the x-axis right through the middle of it again. Does this make sense? So I just took the red disc and brought it out to the side there. We're going to talk a little bit about this because remember what we're doing is we're going to take this solid, we're going to split it up into a bunch of rectangles and then make the number of rectangles approach infinity, therefore making the width approach zero. We'll get the exact volume. Does this make sense? Okay, so now I've got my iPad like this, and I wish I could turn the screen. So maybe you should let's go really high tech now. If I took it, can y'all see the red disc? If I took it and did this, what does the red disc look like now? What geometric figure?
A cylinder.
A cylinder. It's three-dimensional. So to say that it's an oval, that's two-dimensional, right? It's three-dimensional. Doesn't it look like a cylinder? You see how somebody just took like a classic cylinder and did this? They just turned it on its side. So this is really going to test your geometry knowledge. What is the volume of a cylinder, aka a disc? Not 1/3. Say again? There it is. Yeah. You got it. So the volume, and you did a cone. A cone. So I'm actually pretty impressed because my other group, I asked the same question and it was just crickets. It was just like, what's a cylinder? Okay. So volume equals pi r squared h. So here's what I want you guys to see. Is this not the radius? I'll do this. Isn't it the distance from the center, which is, of course, our axis of rotation, out there to the outer edge of the whatever the solid is. So I'm gonna do a little more amazing 3D drawing here. You ready? Is this not part of that representative rectangle? Can you see how that representative rectangle would sweep out this disk? It's a good description, yes? Okay. All right. And then, so that's the R. What about the H?
It's still, it's like the
Isn't the height right there? Okay, so I could put an H right there, and that would make sense. However, let's think back to the kind of the conceptual idea that you guys gave a minute ago. How many of these representative disks would I need? And therefore, the width would be approaching 0. So the width is going to get super tiny. And typically, when we're talking about integrals and all this stuff, and something's getting squeezed down to be approaching 0, we don't represent it with something like that. It would be represented by a different variable. Not D. That's not a bad idea, but I'm trying to get you guys to come up with this on your own. So, I mean, you could put dh, but then the rest of your integral would have to be in terms of h. So it's not d. It's definitely not dr, because dr would be a little tiny change in radius, and the radius is what it is based on the function. So go back to this. Can you see? Oh, okay. So Anna's starting to get there. Do you see how this gray little tiny change in height is represented here and here and here? So wouldn't it also be represented here and here and here? So the width is measured on what axis? So instead of dh or dr, it would be probably dx. Could be dy, depending on how this is arranged and how it's oriented, but it would be either a dx or a dy. One last thought, maybe this might be worth talking about on the radius. I'll go to the red circle, and I'm doing this at risk of cluttering this up even more, but I'll take the risk. See if this shows up well. If boy oh boy, I'm going to make this yellow. Can you see the yellow?
Yes.
Isn't the yellow a measurement from the x-axis up to the top of that parabola-looking thing? So if you start on the x-axis and you measure up, what do we call that? Think very 7th grader-ish. Height, and on the graph like this, height is represented by which variable? So file that in the back of your mind, okay? You really could think of this as a y, maybe. Oops. In some cases, it'll seem to be that way, and it might just be what it is supposed to be. So just file that in the back of your mind. I'm just kind of foreshadowing a little bit. Okay, so a couple of brief principles and then some formulas that you pretty much already know based on what we just did, and we'll do some examples. Okay, so the representative rectangle should always have a particular relationship with the axis of rotation. Anybody have a guess? Okay, I wouldn't know if you would know this from our discussion. It's got to be perpendicular. Let's try that again. Perpendicular. It's got to be perpendicular. Representative rectangle has got to be perpendicular to the axis of rotation. Now for these formulas, I'm hoping that you're going to be able to pick out where these formulas come from. What do you see here, here, and here?
Pi r squared.
Pi r squared. H, isn't dx your h? So this is basically the pi r squared dx is essentially the volume formula for a cylinder. So if you're ever looking at one of these and you're like, oh man, it's one of those solids, I got to find the volume, I forgot the formula, just remember it's the volume of a cylinder. And if you remember that from geometry, it's just pi r squared h. But you got to do an integral, of course, but just pi r squared h. That's really all it is. You can see the same thing, of course, being true if we're revolving around the y-axis or some other vertical axis of revolution. And again, this is just reiterating from the picture. What does r of x stand for? Well, this is the radius. probably could be better said as distance from axis of rotation to the outer edge. Distance from the axis of rotation, ROT stands for rotation. Distance from axis of rotation to the outer edge. dx is the thickness of the disk. And really, honestly, r of y and dy are the exact same things. They would just be in terms of y instead of being in terms of x. Okay. I know you haven't done any examples yet, and you might be thinking, oh, that's when it's going to get difficult. How are you feeling right now? Any questions? Just visualizing, conceptually? All right. So our two examples today are calculator active, so you want to get your calculators out. And I'm hoping that you'll be able to see the nice continuity of all these examples. Do you see how number one is like what I was trying to do with the animation? It's very similar. It's really similar to what I was trying to do with the drawing. Check it out. And if you're super speedy and you get on to example two, I didn't give you an axis of rotation, so hold off on number two. You're getting way ahead of me. Okay, so it says region R is bounded by the x-axis, and the graph of f of x is shown there. It says find the volume of the solid if region R is revolved around the x-axis. So here we go. Just give you a couple of pointers along the way. First thing I'm going to do is draw my little rotation symbol, reminding myself that that is my axis of rotation. You might think, well, gee, isn't it always the x-axis? The answer is definitely not. Then you might say, oh, then it's the y-axis sometimes. And I'll say sometimes, but it could be other stuff too. So always mark the axis of rotation. Yeah. Yes, it's really, you know what, Anna, I can just about guarantee you're going to get it. You'll be fine. Okay, let's see if you remember this from like 2 minutes ago. The representative rectangle should always have what relationship with the axis of rotation? Yeah, I heard it, perpendicular. So here is my representative rectangle. I'll just sketch it in right there. And can you see if I took that fairly skinny rectangle and revolved it? Well, really, honestly, wouldn't it revolve at first? Wouldn't it revolve straight towards you? It would come towards you and then around down to the bottom. If it happened, wouldn't it give you a disk?
Yes.
Okay. So this is going to be probably the most important step of all, because it's going to set everything else in motion. What is the thickness of that representative rectangle? Is it dx or is it dy? It's got to be one of the two, and it is dx. So here's what that means. I know that everything in my integrand is going to be in terms of x. So I'm going to write volume equals pi integral of, I don't know yet, dx. So pi integral dx. I'm going to try to make my pi a little nicer. Okay, there we go. Let me just encourage you along those lines to always write it like this. The number one thing that people forget on one step or another is the pi. There are plenty of people that know exactly what they're doing, and they get their radius right, they get their dx in there, and everything is perfectly set up, but they forget the pi, or later on when they go to the calculator, they forget to put the pi in the calculator. We'll talk about that in a second. But always, if I were you, I would always write it out just like this. We'll fill in the details now. So the limits of integration are basically going to be describing where we start accumulating and where we stop accumulating these disks. Would you guys agree that this is really what would be more or less happening as I start accumulating these? Well, this is looking like a pretty good drawing for once. Okay. Missed on that one. That's okay. Kind of missed on that one too. Oh my gosh. Okay, so where would I start accumulating these disks? At x equals 2, right? And that needs to be an x because I have a dx integral, right? So I would start accumulating at x equals 2. Where would I stop accumulating? 6. That's right. So I'm going to integrate from 2 to 6. Now remember, all this is pi r squared h. It's just the volume of a cylinder. I've got the pi, I've got the h, I've just got to figure out the r. And here's what's different about this than a typical cylinder. Doesn't the radius change depending on where you are? So for example, when I'm over here near 2, isn't the radius, oops, let me fix that. Isn't the radius over there really short? And then as I move towards the middle, now the radius is getting longer, even longer, longest right there in the middle somewhere, and then the radius starts to get shorter, shorter, and then obviously over there it's getting close to 0 again. So the radius isn't just going to be 3 or 10. The radius is going to depend on where you are. Well, how would you describe the radius for this one? Say again? It's the y value of the function. We're going to use the function. It's f of x, isn't it? So if you put, like I think you would be excused if you put y squared right there, but that's not a good finishing place because everything has to be in terms of x, right? So instead of y, I would put the actual function. So you could put f of x if you wanted. I'm just going to put this because I know that we're about to use our calculators anyhow. But if you just put f of x, that's totally fine too. This is it. The radius depends on the y value. Well, that's the y value. So in your calculator, can I give you some advice again real quick? Just based on lots of experience. When you go to your calculator, don't push math 9. Push pi math 9. Way too many people, they do math 9, they're like, just multiply by pi in the end, and they don't. They forget. So go pi math 9 and then put all the other stuff in there. Should be in good shape. I think I remember the answer. So once you get an answer, let me know and we'll confirm what it actually is. I think that's right. Yeah. I think that is right. That's what comes to mind from the other class. Do you guys get that 107.233? Okay. The other class got that too. I'm pretty sure I did as well. Okay, so just a quick check-in here before we do our final example. Where do you sit? So far, so good? Any questions? Be a chance to say something. Type. So I know it's a good question. So there's kind of a chain of thinking there. So how I arrived at being in terms of x is this. This is where kind of it started. It said, find the volume of a solid if region R is revolved around the x-axis. So I know that my representative rectangle has to be perpendicular to the x-axis because I'm revolving around the x-axis. So if you're revolving around a horizontal line like the x-axis, it'll always be a dx. If you're revolving around a vertical line, like in just a second you're going to see the y-axis, now it's going to be dy. And that, of course, sets everything else up to be either x or y, depending on which one it is. Is that helpful? Okay.
Honestly, like...
Okay, here we go. Let's look at our final example. Number 2. Like I said, number 2 has an omission typo. Notice how I never gave you any sort of an axis of rotation. Or really, to be honest with you, I never even gave you really a directive, like find this. So how about this? This is how this one would go. It'd be something like find the volume of the solid if region M is revolved around the y-axis. Find the volume of the solid if region M is revolved around the y-axis. This would be a nice kind of a segue from what Ty just was talking about. And it's the same question I asked you 5 minutes ago. What's the relationship between the axis of rotation and the representative rectangle? Perpendicular. So instead of drawing a rectangle like I did on the last one, this one would actually look something like that. So now the thickness is no longer measured on the x-axis, it's measured on the y-axis. So what kind of a rectangle would this be? It'd be a dy. So this is decided early on. Like if you just sketch into your picture this representative rectangle and recognize, hey, the thickness is measured on the y-axis, so it's dy. Here's what that means. Volume equals pi. I don't know why I can't draw a pi this morning. There we go. Pi integral dy. Pi integral dy. Our job then would be to fill in all the details. I'm just going to start sketching in some of the representative rectangles. Uh-huh.
So that's the fact that this is dy. Is there any other distinguishable factor when we're typing it in the calculator and finding the volume? Like distinguishing it from dx?
So your calculator is just going to take whatever input variable you give it. And so it just wants an x. So like as you're typing it in, it's going to show up as an x, but you know it's a y.
Right. But
Yeah.
it doesn't, like, the dy and the dx really has nothing to do with the problem except for just saying.
Oh, it has everything to do with the problem.
Oh, yeah.
As far as your variables, like when you're talking about like if you actually find the antiderivative.
I mean, just, these are almost the same, just when we're just finding the volume of it, except
Oh,
this is dx.
The concept is no different.
Yeah.
Yes, the concept is exactly the same.
Yeah, okay, that's what I mean.
Yep. Yeah, you're still going to be using pi r squared. Look at all my rectangles. I just about got it all filled up. That was fun. Okay.
Why? You're talking to me.
Hey, I got to get my limits of integration there. I got to define where I start my accumulation of these and where I stop. Where would I start accumulating? And where would I stop? It's basically when x is 0, isn't it? So you could put whatever decimal you just said. I'm going to put e to the 2 minus 1. Right, I just plugged in a 0 for x. That's probably that 6 point whatever number you guys said, right? Okay. You guys ever been to Disney World?
Nope.
Disneyland? I went there when I was like 17. Not that exciting.
Never been.
Anyways, have you ever seen the castle at Disneyland, a picture of it? Wouldn't this, like if this did get revolved around, wouldn't this look like the tops of the castle, like the little tops of the towers? It's kind of like, almost like a curvy cone, I guess. Kind of an interesting figure. Okay, so then what goes in for the integrand? Can I show you the wrong thing? Y'all ready? This is the wrong thing.
Because it needs to be in terms of y.
It has to be in terms of y. So that's wrong. That's for sure wrong. What could I do to get my radius in terms of y instead of x? Solve for x. That'll get me there. So that's not going to work. This will. If I take this, and I'll just do this quick. I'm relying on your incredible algebra skills. I'd go y plus 1. How do I deal with an exponent that's a variable? Natural log in there, yep, so it'd be natural log of both sides. This would give me natural log of y plus 1 equals negative x plus 2. And let's see here, it would be negative natural log of y plus 1 plus 2 equals x, if I deal with those last few details. This is actually what goes in there. Don't forget to square it. And then I believe the correct answer is 15.011. 15.011 if you enter that into your Math 9 correctly. These classes go by way too fast. Brennan?
Do you not need to have the absolute value on y plus 1?
Nope.
No.
No, I just solved this as is. Like this would be more of, like the solving for x would be more of like a pre-calculus question.
Okay.
Yeah. Yeah. Okay, why don't we spend the next week or so working on volume?
Yeah.
Love looking
Actually, yeah, like a week of class, something like that. Hey, tomorrow we'll continue with volume after we do your area quiz. We'll get into your test stuff at the end of the week. Have a good rest of your day.
Mr. Anderson is big